Hello everyone, welcome to the third talk in the Algorithms for Data Analysis series. Today we have Apoorv Namjoshi from BSMS 2021 giving us a talk on Monte Carlo methods and simulations. Over to you, Apoorv.
Okay, thank you, Sasi. Yeah, so today's topic is Monte Carlo methods, as mentioned. I'll start sharing my screen now. Is it visible?
Yes, your screen is visible.
Okay. So let us start with this. So Monte Carlo methods is there is no clear cut definition for that. It is a general class of methods which uses principles of inferential statistics to estimate values of an unknown quantity, and there are two words that we might use frequently in the stuff that we do next. So kindly take a minute to read this. Okay, so regardless of what specific steps are followed, there are three general steps for any Monte Carlo method. So they are the following. Firstly, define the system. Uh, right now, this definition might seem a bit abrupt, like these steps which I write, but once we start doing the examples, I'm sure it will become much clearer. So I will keep going back to this definition for every example that we do. So the first step is define the system and identify the dependent variable, which is what we have to find. Uh, and the independent variables, which will have to be taken into account when we make our inputs. Secondly, define the distributions of the dependent variables, because all of these are random variables. And thirdly, mm, one second. Okay. Hmm. Okay. So yeah, so we start by defining our system, identifying the dependent variable, which is what which is which decides the result that we want to get, and the independent variables which decide the input. Define the distributions of the dependent variables and run simulations. Uh, Now, before we get straight into the examples, I might introduce first the history of how this came up. Mm, yeah. So this was even though certain instances of this method have happened before earlier, it was conceived by the Polish mathematician Stanislaw Ulam in 1946, and it was conceived as an alternative. and not a sort of algorithmic way to find out the probability of certain events in solitaire, and it was alternative to abstract thinking. So the key idea that was involved here was to actually like simulate the game and use simulate the game of like a very large number of times, and to interpret the probabilities based on the results that we get. To quote him, after spending a lot of time trying to estimate, wait, huh, yeah. The first thoughts and attempts I made to practice the Monte Carlo method were suggested by a question which occurred to me in 1946. The question was, what are the chances of that a Canfield solitaire laid out with 52 cards will come out successfully? After spending a lot of time trying to estimate them by pure combinatorial calculations, I wondered whether a more practical method than abstract thinking might not be able to lay it out, say 100 times, and simply observe and count the number of successful plays. This was already possible to envisage with the beginning of the new era of fast computers, and this was then further applied to mathematical physics, and the actual calculations were begun in 1946. Okay, so I think with some examples we'll be able to understand this better. The simplest example that we can start with is integration. Suppose there is a certain function over a certain range. Okay, now normally how would you integrate any such function? Suppose these points are called P and E. In general, given this information, how would you integrate a function? Did somebody? Uh, okay. I am not. I was referring to the Riemann method actually, Sahil, because what we will do ahead of this is like closer to the Riemann method. Which one are you talking about? Mm, no, no, I don't think that is relevant here. Okay, so what you do in the Riemann method is you create a partition, that is, you introduce these intervals here between A and B, and you introduce these rectangles. and so forth. Now you will first calculate the lower sum. All of these rectangles have to be of the same size. So the width has to be a certain t. And then like you will have the intervals a plus t, a plus 2t, and so forth. And then you will calculate the lower sum as well as the upper sum and find the like value at which they converge. But when you use Monte Carlo methods, what you do is the following. Instead of taking intervals with like with intervals which have like which are equally what to say, okay, simply put, instead of taking triangles of equal width and you take any random selection of points here, like for example one point here, another one here, another one here, another one here. Then you similarly draw rectangles. Okay, the function I've drawn is a bit weird, which is making this inconvenient. But as the intervals become smaller, you will get more accurate figures. Because here we are using very few points. So using Monte Carlo methods, what we essentially do is take many such collections of random points between somebody said something. No, okay. Hmm. Many such collections of random points, find many such sums of the rectangles generated by all these points, and find the average value of them. And the larger number of random sets of points that you take, like, or rather more you repeat this experiment, the closer you will get to the actual value. Let us now move to another problem which has been done using code. I will briefly introduce the problem here. Suppose here we have a square, and inside it we have inscribed a quadrant of a circle. So the radius of the circle is equal to the side of the square. Now, a given result that we have is the following. Okay. The other area of the quadrant, not the entire circle. Okay. One thing, and now based on this result, what we need to do is find the value of pi. And one thing which I think we can agree on here is that the area of the quadrant or any region, as a matter of fact, within the square is equal to, no, okay, not equal, it's proportional to probability of a random point in the square being in that region, in this case the quadrant. Okay, I would like you to take a minute to go over this before we move on to the code. Is this does everyone agree with this statement? Eh, any issues with this? No. Okay, now we'll move on to the code. mm, 1 second. Okay, can you see the code? Hello.
Yes, your collab is visible.
Okay. Okay, so what we are doing here is, let us start with a small n first. We are considering n random points within the square. These variables represent the x. This is a list. X coordinate is a list. It represents the x coordinates of the random points. And this represents the y or and we are considering the square to be of side 1 unit, and one of the vertices is the origin. It is there in the first quadrant. Okay, I think I should specify that in the problem statement. I'll show it once more. Okay, so this square which we have described is located in the first quadrant in such a manner, and so this quadrant is the uh, first first quadrant of the unit circle. This is the y-axis. This is hmm. Okay. Now back to the code. This array will store all the this list will store all the x coordinates of the random points. This one will store y coordinates of the random points, and we are considering n points. We are distributing n points inside the square. Let us start with a small value of n, and we'll see what happens as n increases. So here, this is the same thing. For I in range 1 to n, we add a value to the list of x coordinates, which is a random value from 0 to 1. And in this way, we will have a n random x coordinates. Similarly, we have n random y coordinates here. And if the distance of the point from the origin is less than 1, then it means that the point is located inside the quadrant. So in that case, we have this variable inside count, which is number of random points located inside the quadrant. We will add 1 to this variable for every point which is at a distance of less than 1 from the origin. And at the end, we will calculate the ratio of the number of points inside the quadrant to the number of points outside the quadrant. In the square. Okay. And that is given like this. We are approximating this ratio, and it is given to us that the ratio is equal to pi by 4. So based on that, we can uh, find the value of 4. Now for 10 such points, we run this program, and we got the value of pi as 2.4, which is not very accurate. Because, okay, now I take 100 random points inside the square. I run the same program. Now it is 3.16, which is closer to pi, to the actual value of pi. Now I run it 1,000 times. I mean, I use 1,000 points randomly distributed in the square. Now it is 3.14, which is even closer. And as I keep increasing this, okay, yeah, I think the number of decimal places is limited. As I keep increasing the number of points which I am scattering in the square, the value will become more and more accurate. This is
ரெண்டுத்தையும் ஒட்டா படிச்சிங்கன்னா அப்படியே போயிடலாம். அப்புறம் புக்கில் இருக்கிறது எல்லாத்தையும் ஒட்டா படிச்சுக்கொண்டு
uh, could you please mute yourself? Okay, thank you. So as we increase the number of points that are distributed, the number of random points that we distribute across the square, we get a more and more accurate value of pi. Can this be used to, one second, can this be used to calculate other constants like exponent? Sorry, can you elaborate a bit? You can speak if you want. Okay, do you mean E? Or yes, pi is 3.14. Okay, go ahead. Okay. The reason we were able to calculate pi here
Apoorv, you're muted if you're speaking.
oh yeah, sorry, I forgot to unmute myself. Huh. Okay. Pi is 3.14. Similarly, other universal constant. So what I was saying was that the reason we are able to calculate pi is due to this result. Due to this result and the fact that the area of the quadrant is proportional to the probability of a random point being there. If you can come up, I mean, this is a result that we consider as given for the purpose of this problem. So if there is any other constant that can be um, expressed in terms of any such result, then it doesn't hurt to try. Do you have like any example in mind? Maybe you can try it out right now. You can think. Yeah, you can unmute and say. Okay, okay, you can type. Go ahead. We can think of anything which have area in terms of E. Okay, so if you can come up with a problem where uh, any ratio of ideas can be a ratio of areas can be represented in terms of E, then maybe we can estimate that. I do not know of any such example, but theoretically we should be able to do. Okay, fine. Hmm. Okay, so I would like everyone to just let this sink in for a minute. I'll show the code again and you can ask me if there are any problems. You can see the question, right? Hello? I guess you can. Coming back to the code. Okay, I guess we'll move forward now if that's okay with everyone. Okay. Another problem which we can tackle is the following. Suppose a fair coin is tossed 10 times. What is the probability of getting 3, 6, or 9 heads? Now, the standard method to solve this would be to simply use the binomial distribution for probability, So you can use this formula, ncx into probability is equal to ncx into p raised to x q raised to n minus x. And this you can calculate for 3 and 6 and 9. So you get 10 trials in total. Probability of heads is 0.5 and 3 heads, plus the same for 6 heads and 9 heads. This roughly comes out to be around now. This is the abstract method by which you get an exact answer. The 0.3 is an approximation of this, but if you calculate, you will definitely get some uh, value, some exact value. What we can do instead using the Monte Carlo method is this. Essentially, what we will do, mm, 1 second, where is that? Can you see my collab screen? Hello?
Your collab screen is visible.
Okay. Okay. So what we do, we define a single trial of doing the experiment 10 times. I mean, tossing the coin 10 times. We record the number of heads that we get. Uh, yeah, this is the outcome of each toss. This toss coin is a method that randomly gives heads or tails. So in one such trial, we find the number of heads we got. Then the same entire trial of tossing the coin 10 times, that is repeated again and again, and every time for the number of times we get the results we want, we keep this variable t. Every time the result is either 3 or 6 or 9, we increment t, and then we conduct another trial. If we conduct a large enough number of these trials, then we should start approaching the answer. The this m, which is the number of times we conduct a single trial of 10 tosses, has to be sufficiently large, by which I am not sure how large. Even if I use large values, I am getting problematic answers. But in principle, the closer this goes to infinity, the closer you will come to the value of 0.3, which you got based on calculating. So these are two ways of solving the same problem. I will display the problem statement once more. I think I can. Okay, so we looked at this problem in two ways, one in the conventional way and one using Monte Carlo method. So these were two basic examples. Now one more thing we wait, what is this? Okay, there are some questions. Wait. Uh, is it exactly so many heads? What do you mean by that? I mean, if you're talking about the 3, 6, and 9, that those numbers are just part of the problem statement. You could substitute any value between from 0 to 10.
No, what I meant to ask is like, are you stopping the experiment after so many number of hits,
No,
or
you will do the experiment, like you will in one trial you will do 10 tosses irrespective of what you get. The
so you're
favorable outcomes for you are when you get 3 heads or 6 heads or 9 heads.
so out of them you are just calculating after the performing the
Yeah,
entire experiment. You're
yeah.
calculating this, right?
Yes.
Yeah, that's fine.
Okay, fine. Obviously, there's multiple methods to get to the same constant, especially when all you have to do is represent it and an integral to do a Monte Carlo simulation. Yeah. Okay. Okay. So the next part of this talk is based on an astronomical application. This is based on a paper which I found. I will link this paper here so that you can look at it while we go about this, because there are two parts which are relevant and they are not on the same page.
Um, Apoorv, if you're speaking, you're muted.
Okay. Huh. Huh. So I would draw your attention to this paragraph where the problem statement has been outlined. That's what I was saying. Consider projectiles of negligible dimensions. Projectile is what is the thing which is colliding with a given planet, and target planets that are massive enough to induce gravitational focusing at close encounters. Apart from this, both targets and projectiles are assumed to move on elliptic Keplerian orbits around the sun. Now, every elliptic orbit will come with its own set of independent variables. Consider a planet with a given orbit. A projectile performing one orbital revolution may or may not collide with the planet depending on the exact values of its orbital elements, and finding the outcome is then a deterministic problem. If the values are not known exactly, as is always the case in reality, we face the well known problem of estimating impact risks for observed near Earth objects at upcoming encounters. However, our goal is different since we are interested in a huge population of projectiles with a wide distribution of elements, and we want to find the random probability of an impact per orbital revolution which corresponds to this distribution. Okay, now the dependent variables here are the semi-major axis of the projectile orbit, eccentricity, inclination relative to the orbital plane, denoted by A, E, and I. Three remaining elements, longitude of the ascending node. Okay, ascending node is a point with reference to the reference plane with respect to which the elliptical orbit is seen. The sun is supposed to lie in the reference plane, and the place where the elliptical orbit intersects with the reference plane is called the ascending node. Argument of perihelion omega, that is the angle when the object is at perihelion, and time of perihelion passage are treated as stochastic variables with uniform probability distributions on the intervals 0 to 2 pi for omega and capital omega and small omega, and 0 to pt for t, where pt is the orbital period of the target, which is defined here along with all these quantities. And this paper actually uses multiple methods, but we will focus on the Monte Carlo one. Okay. This is the Hill sphere method. For a given combination of A, E, and I, we take a vast number of triplets, omega, small omega, and tau, using the relevant uniform distributions. Okay, so these are the simulations you are running for a given orbit. Each of these triplets then define, like you're considering the projectile and the planet at various locations along their orbits. Each of these triplets then defines a Keplerian orbit for the projectile. We trace this motion along with that of the target over one projectile orbit, checking for close encounters. Here we can choose between two different approaches. One uses the unperturbed Keplerian orbit of the projectile, while the other uses the elliptic restricted three-body problem. Okay, so in this method, they are using the Hill sphere, and the Hill sphere is basically a region around the planet within which it can effectively attract a satellite, and it is not affected by perturbations from other larger objects. It is well known that impact probabilities with terrestrial planets are no larger than roughly the order of 10 raised to minus 8, and therefore they are using the Hill sphere, which is a much larger region. So the probability of the projectile entering the Hill sphere will be much larger than the probability of the object actually striking the planet. But there is a scale factor with which we can convert between the two. The real target, which is the collisional sphere, is replaced by a much larger standard target for which we choose the Hill sphere with a given radius. This is the theoretical part. We are not going into it in detail, but what you need to know is that the Hill sphere is basically concentric to the planet, and it is larger than the actual planet. Using sigma collision and sigma h for the cross sections of the collisional and Hill spheres, the number of hits onto the Hill sphere may be rescaled into the number of actual impacts, because there is a like I said, there's a scale factor which helps you convert between the actual probability of collision and the probability of entering the Hill sphere, because everything that enters the Hill sphere will not necessarily actually collide with the planet. And this S collision has to be evaluated separately for each hit using the specific value of u, which is the relative velocity of the two bodies. And this is the estimate you get for the average impact probability. And for u, uh, the, and this is calculated using all the possible triplets of the independent variables that you took, which will represent the probabilities of colliding at any position on the orbits. So the takeaway is that, let me share the definition again and see how far we stuck to it. Hmm. Firstly, to define the system, identify the dependent variables and independent variables, like which were more explicitly defined in the last example. Define the distributions of the dependent variables and run simulations. And the run simulations part has only become possible in the last 70 to 80 years, when computers were invented, because the date around which these methods were actually put into practice coincides with the invention of the first computers, which were very large and they could run many simulations. So this was not really manually possible for most of history. So this third part is the like real breakthrough here. And in the quadrant problem, the variables were the coordinates of the points, and they had a certain range. In the coin tossing one, it was a binomial random variable. And in the third example, the variables have been explicitly described in the paper. So that is about it. It's a bit tricky to come up with more examples, because most of the examples are either very advanced or like not rigorous enough. But that is kind of the whole spirit of Monte Carlo. You don't really, I mean, it is not possible to truly understand unless you actually go over all examples. So I'll stop sharing now. Does anyone have any questions? Okay, go ahead.
Yeah, so I had one question.
Mhm.
So in the examples you used, everywhere you have used like all of the events are equally likely or having some sort of uniform distribution.
Mhm.
And the first step we need to know is not even first step, like just identify variables, and one of the steps is finding the distribution itself. So can you shed some light on what are the ways you need to find the distribution? Like how can you do it?
In most cases, you already know the independent variables, because the independent variables are associated with your input. But in the cases which I studied while preparing for this talk, most of them had followed conventional distributions. I have not really gone to a point where like the distribution cannot be quantified. Do you have like any examples in which you would have to find the distribution or something like you're saying?
Yeah. So for just example, one of the examples in physics itself, we can take like Maxwell speed distribution. We already do know
Okay.
what does it look like, but
Yes.
suppose we didn't, and then how would you go about solving this sort of problem?
I mean, this sort of problem, as in you are talking about, say, root means square velocity or things like that.
Yeah, in any property. Yes.
Huh. Okay. So, the experiments you would have to conduct, a large number of times, that would involve measuring the speed of each and every molecule in some way. Like you would have to take, suppose, you take a certain 3D space. In that space, you would have to find a way to measure the speed of each and every molecule at a certain temperature. I think maybe the way the distribution was found, that like a similar approach could be used. Was it derived experimentally or?
I think there was theoretical explanation for that, like
Okay.
from the number of states.
Hmm. Yeah. Okay, but like,
So it's like
yeah,
do you
my
already.
best guess is this, that you would have to find the speed of each and every molecule, because that is the whole point of Monte Carlo use. Yeah, but to you would also need a range for the speed, which would probably be determined by things like temperature and all. But yeah, I mean, this is a case where a lot of things are involved, so it's a bit difficult to say offhand.
So you need to know already need to know the distribution for performing the simulation.
Yes.
All right.
Okay. This is it. Does anyone have any more questions? I will share the codes after this is done.
Okay, here's a question.
Okay.
Okay, why is rand? Okay, what exactly is the advantage of Monte Carlo methods? Like, why are we taking random sampling and thinking I mean, telling it's better than uniform sampling? Like, oh, okay, like going back to the example of the integral,
Huh.
we see that the Riemann method works well enough. How does the would how would random sampling improve it?
Uh, I mean, in case of integration, maybe it does not make much of a difference. But I mean, it all depends on the kind of function you are dealing with. Some functions would be more difficult to integrate in a theoretical manner, because when you use a Monte Carlo method, you actually simulate. It's not something you can like just calculate theoretically, right? That is why this method was not used until the last 80 years. So automation is in some ways the main advantage. Because you cannot generate random numbers yourself. Like you can, but till what extent?
Yeah, that makes sense. Or I mean, you can automate it, but you can even automate the Riemann method with the for loop. Oh, in Riemann method, you are taking a uniform sampling. I mean, where all the
Yeah.
points are equally spaced out.
Hmm.
So what exactly is the advantage of random sampling, which is what you do in Monte Carlo methods?
Okay, that I'll have to think about. I'll try to get back to you.
All
I'll
right.
also like send the answer on the group as when if there is any such clear cut advantage.
All right. All right.
Thanks for the question. I'll note that down. Anyone else? Any more questions?
Okay, if there are
Okay.
no further questions, I think this might be a good place to stop. Thank you for the wonderful talk, Apoorv. I'm sure everyone found it informative.
Yeah, I hope so. Thank you for attending.